Yeah, good afternoon, ladies and gentlemen. Thank you, Gabi, for invitation to this outstanding event every year. And now it gets disastrous. Not yet, but if we don't have a closer look at these things, we will see some disasters in digitization. So I put some ideas together what we have to look at when we think about digitization in the next years. What really threatens this digitalization? I put together three things. First, cryptography. Why cryptography? So that's quite clear. If cryptography doesn't work anymore, we will be in trouble. So there are threats to our current cryptography. I will give some ideas about. We rely on that. We do encryption for privacy. We do authentication to identify people in the digital I talk to. So we need strong fundamentals in cryptography that do what they promise to do. Second, business models. The current business models tend to be very monopolized. I will give some idea what that means and why we should have a close look at this. Everything's getting to be as a service. You get APIs, you get access to software in cloud environments, and you do not have control over the software anymore. So this is something we have to think about, what this means for business models and how to work with software and with computers today. And third, climate. What? Climate, okay, another topic that is in the media, that is, we saw just that picture from Donald Trump here. Yes, and digitization is also very strongly related to climate because it costs energy when we run a lot of computers. So, interesting things. And so why three things? Because I thought it's good enough for 20 minutes. I can easily put many more things on the topics, but so these are already very challenging to look at. First, the technical thing, the most technical thing in these three topics, the quantum computer threat. I've named it this way. Yeah, almost everybody has heard about quantum computers. Maybe not so much what it means, what quantum computers are. So when we look at classical computers, to compare that, we quite good know what they do, how they work today. They are built on 0 and 1, on two states of electrons. And we have a very high density integration of that. Today we have trillions of transistors on a very small chip or in computers. And we quite well know how they scale and how we can scale algorithms on that. And what we know today from our cryptographic algorithms, they cannot be broken by current computers because the scalability doesn't allow us that. Algorithms, at least what we use today, are constructed in a way so that these computers cannot break them. So, for instance, RSA, maybe you know that algorithm for signing by asymmetric key pair is based on factorization of large numbers that is not cannot be done efficiently with the current computer. And if the number is big enough, so we have about 4,096 bits for RSA today that claim to be secure. If we do not have an easier way to factorize these numbers, we are safe with the current computers. But when we look at quantum computers, the situation changes because we do not have these two states anymore. We have a continuum of states because of this quantum bits, of these qubits. They are different to zeros and ones we have today in the computer. And that scales dramatically better than the current computer for specific problems, and that's very important. Quantum computers will not replace the current computers, but they will be much more efficient for specific problems. For instance, for simulations of chemistry processes and so on. A small number of qubits already is good enough to simulate a lot of different things simultaneously. So for instance, 50 qubits can model the same amount of states than 1 trillion of classical bits in a computer, because it scales in the power of 2, so 2 power of 50. So, okay, 1 trillion seems to be not that much. It's much less of the atoms of the human body. But to give you an idea how that scales, just at 190 qubits, so we are at 260 qubits, it outpaces the number of atoms in the universe. It's 2 power of 260 then. So we have a much better scaling with this quantum computer in specific problems, and this will help a lot to simulate things, to do a lot of good things. But unfortunately, in 1994, I think, there was some research already on the kind of algorithms. Someone named Shor constructed an algorithm to factorize large numbers. What does it mean? We are done with RSA if we have such a quantum computer. So for cryptography, quantum computers is a real threat, and we have to care about that with actions today, so that we do not run into this disaster. So what does this mean? Be prepared. So we have to take care that there will be some quantum computer sometimes. Maybe there won't be someone. So physicians are not convinced, some of them, that it will happen. And to be honest, we are in the state of inventing the transistor on a quantum computer, as we have been 100 years ago or 80 years ago for the silicon age. But we do not know how that improves and how fast it will go. So we have to be prepared, and cryptography has to hold for many years in some cases. For instance, for 30 years in some classification levels, we have to protect data with cryptography. And so we have to develop algorithms already today. That's something's already in work. The NIST has started a challenge, and there are a lot of also European algorithms put into this challenge. But it's not only the algorithm that's very important. We have to look at the implementation also already today, because the current protocols are not fit for post-quantum cryptography. The reason for that is that key sizes of quantum algorithms or quantum-safe algorithms are much larger than we have today. So if you look at this diagram, it's logarithmic, you see. So we have key sizes of some thousands of bits, and we cannot handle that in the current protocols. So we are very active in this implementation side from a company point of view. We are active in this standardization side, in the ITF, for instance, and that's very important to be prepared, make crypto agility happen in the products, and look at the standardization process. Okay, the second threat, the business model threat. Okay, so as a company, you can be too late. For instance, selling music cassettes, even with MP3 and streaming today. Maybe that doesn't work anymore. But what I mean is that the business models that we see today, and that are very successful, by the way, everything as a service. When you use your cloud service, software becomes accessible only by APIs. Software doesn't run on your own computer anymore, well, some, but the way your data is processed is done on a server that you do not own anymore. the program and the software that's working with your data runs on that server. You do not know where it is, you do not own anymore. You just put your data somewhere and it's processed and you get some result of that. These software stacks become more and more invisible, and this is sort of threading the way how you work with your data, because when we look at the companies that do that, the big public cloud companies, for instance, they monetize on that data. They monetize on the efficiency gains of these big infrastructures they built. And so we put the data somewhere. It's very easy, it's very convenient, but we get out of control what's happening with it, where it is processed, and what the software really does. You do not have any control of that anymore. And these cloud providers or this industry monetizes a lot on this efficiency gains. So it's not only to hold back the software and to provide you only an API to that, but it's the efficiency of cloud infrastructures is obvious. So you provide compute power to many people. You can distribute your compute jobs, and you can efficiently use these computers. So it's very efficiently from a technical point of view, and also from a business point of view, because you can sell your compute power in a different way, and you can oversell it. Like, for instance, telcos oversell their capacity of their infrastructure. So you can oversell your capacity of compute because it's statistically computable how much compute power you need in average. So I heard a number that is very interesting, as the big cloud providers invest $1 billion a month into compute power yet today. So they already invested $100 billion, and each month $1 billion compute power is built at top of that, and this makes compute power very, very cheap. And they sell it more expensive, of course, so they make a lot of money off that. And it still is cheap compared to an on-premise infrastructure. So when you are, from a business perspective, you are pulled into this cloud infrastructure because it's very cheap. So it's sort of self-accelerating process here. That's sort of a threat, I think, in terms of getting out of control what happens with your data and what software is running somewhere. But what we can do. So we have to get back into control, of course. These cloud stacks, these big cloud providers run are proprietary. They use it in their own cloud infrastructure, and they do not expose, or they do not sell that software to you. You cannot run that on-premise anymore. We have to get something, or we have to build something that allows you to run cloud-like infrastructures, cloud infrastructures on-prem or in a different way that these big cloud providers do. And another trend, I think, the edge cloud concept, that is very interesting to relocalize workload. So from a technical point of view, edge cloud is motivated by low latencies. You need to have your compute power close to your client, because the computation must be done very quickly, and the result must get back very quickly. Self-driving cars, the known example for that. So compute power must get back from centralized data centers to the edge. And this makes it more local, and this makes probably more business models for local providers attractive again, but they need their own cloud stack to provide that, the way of sharing this compute power, to share the infrastructure between different tenants in the same way as the big cloud provider did. So Another trend, the appization, I call it this way. So the trend is that working with your data becomes more specialized. So you have your app for, let's say, local traffic. You have your app for fitness, for whatever. You have apps for for everything, but you have your specific app for a specific task. So the specialization of programs becomes more and more relevant. And so it's more easy to get back into control of some software stack and software functionality, because you can specialize on features, on functionality that is small enough to not replace a fully fledged Office package that is huge, of course, but data is more fragmented and differentiated into different use cases. And we have, this is part of this cloud stack idea, we have to invest in open source based infrastructure and platform as a service concepts and models. What we do as a company, so we do a cooperation as Keynote with a company that does water-cooled computer systems. I come to that in the next point. And founded a company called SecureStack, which deals with secured OpenStack infrastructure. OpenStack is an OpenStack cloud stack that can be used by everyone. And there's another interesting platform as a service and very dynamic developed platform as a service thing. I don't know how to call it. It's Kubernetes, which is sponsored and financed by Google, interestingly enough. But this also allows for implementing platform as a service. And we can use these security mechanisms we built there for infrastructure and platform as a service, and provide a cloud stack that can be used on-prem or in different business models. So finally, last but not least, the climate threat. Okay, Thursdays for Future today, but well, no, honestly, it's a really huge challenge, this climate thing, and digitization. I think maybe not scientifically proven, but is part of the problem at the moment. It can be part of the solution, but in the moment, it's part of the problem because we have a lot of compute power, data centers, whatever we build on, and networks. So the amount of energy used for compute is really increasing. And this is an interesting diagram I found at Nature magazine that shows the exponential growth of energy use in the next future. In different places or different environments. So the blue thing, the networks get much more energy consumption. The production of computers and the consumer devices stay more or less the same. So this shows an interesting effect. They get much more energy efficient, but the number increases. So you have a zero net effect, something like that. And the green side, the data centers. This is really also amazing how, in paragraph, how the energy consumption rises with the increasing numbers of data centers. So I think we have to care about the energy efficiency of compute and networks a lot more than we currently do. And we are not very good in reusing energy at the moment, so we heat the environment by data centers, so it's not the best idea to build that in Nordic regions, how big cloud providers do that, because they save cooling energy, so they can better cool their system by the cool environment, but it heats the icebergs. It's not the best way to save energy, I think. And on the other hand, these mechanisms I talked about, like cloud is already a way to make it more efficient, because you use this infrastructure in a shared way. You do not do not use your idle computers for 1% the time they could compute, but they can compute a lot of jobs. There are intelligent ways to distribute compute jobs on different compute nodes to efficiently use that compute power all over the place. And software-defined is another way, so you can reuse hardware for different purposes. Because today you have a lot of specialized devices. In the future, you can use one generic hardware for very different purposes. We can already do. But I think we can do better. We have, as I said, this partnership with this company, Cloud and Heat, and their idea is to use water-cooled systems, which is not new, but they have a very efficient way to do that. But think now in combination with cloud and edge cloud concepts. We can distribute compute power, and we can reuse energy where it and heat from the computers where it exists, where it comes out of the computer. And the idea is to use that water to heat buildings, for instance. So just a very easy idea, but building data centers doesn't make that happen. Building edge clouds and building, in the end, computers in each and every house and heat the house by that way could be interesting. But it doesn't make sense to have a computer somewhere if you cannot use it. So we need very speedy networks, very high-speed networks to distribute that compute power, and these cloud stacks and cloud mechanisms to use that compute power very efficiently. So here it comes together, cloud stack that is available for different business models than the big cloud hoster has, and the energy efficiency, and to use energy where it's otherwise wasted. So we have some solutions. We do not have to go into the disasters I promised, but we have to take a look at this today. We have to do a little research, what code does in a very intensive way, post-quantum networking, software-defined, whatever, and security issues around that. We have to explore new business models with cloud-based computing, and we have to look at these business models in a way that we do not follow these big paths into the one or two cloud providers like the lemmings, but to take a little bit of a risk to say we try it in a different way. And we have to look at the total cost of ownership, even in terms of energy consumption and reusing energy, so that we have to take that into account. That's what I wanted to give you as an idea, and don't be pessimistic, be optimistic that we avoid these disasters, but we have to work on that. Thank you.